A student lab manual may give you an indication on how long it will take a chemical reaction to go to completion. If this information is not available for a specific compound, then how do you know exactly how long it will take the reaction to go to completion?
Today, the most common scientific way to monitor the progress of a reaction and to find out if more than one product is formed is by using a technique called chromatography. Let's learn the steps by watching the stagehands do it.
The most common method for monitoring reactions is thin layer chromatography. Abbreviated TLC, it is used largely as an analytical technique for determining the purity of materials and for preliminary identification purposes. TLC requires very little sample. In this type of partitioning chromatography, a thin layer of adsorbent is coated onto a backing support called a plate. The TLC plate is loaded with material to be separated, and then it is developed by allowing solvent to pass through the layer of adsorbent on the plate by capillary action. The two most commonly used adsorbents are alumina and silica gel. The mobile phase can be any solvent or mixture of solvents that will move the compounds on the solid support. Eluting solvents of various polarities have differing abilities to displace solute from the active sites of the stationary phase. Generally, the more polar the solvent, the more efficiently it competes, and the more quickly the solute will move up a TLC plate. This property, the ability to displace solutes from adsorbents, has produced a list of solvents in order of polarity which serves as a guide for choosing a solvent for a particular separation. The equipment required for this technique includes your sample, the TLC plate, a micropipette, a solvent to dissolve your sample, a developing tank, solvent for the mobile phase, tweezers, a method of visualizing the developed TLC plate, in this case an ultraviolet lamp, and a ruler and a pencil. For TLC, as the name suggests, the adsorbent is supported as a thin coating on a flat surface such as aluminum, glass, or plastic. Remember to always use pencil when marking a TLC plate. Mark a light pencil line about 1 centimeter from one edge, the bottom of the plate. Touching the plate lightly to hold it in place, mark ticks on the line about 1 centimeter apart to indicate where the sample will be spotted. The most useful size of plate for TLC analysis is one of about 8 by 2.5 centimeters. This size permits 2 or 3 samples to be spotted onto the baseline and has sufficient length to give the best resolution in a convenient amount of time. In the second step, you prepare the sample. In order to perform a TLC analysis, it is necessary to introduce a very small quantity of your material onto a TLC plate before developing it. Make a solution of a small quantity of sample by dissolving it in the least polar solvent in which it is readily soluble. You are now ready for step 3. Apply the sample to the TLC plate. There are 3 sample compounds for analysis. Label 1 tick for each sample. Dip the narrow end of a micropipette into the sample solution, causing some solution to rise into the tube by capillary action. Touch the loaded pipette lightly onto the silica surface at the appropriate tick point. This will cause the liquid in the pipette to be drawn onto the adsorbent, forming a visible ring of solvent. Repeat the spotting procedure, keeping the baseline spot as small as possible. Allow the spots to dry either by standing in air or by blowing gently on the plate. You want a small diameter spot. With experience, you can judge how much sample is necessary. Too little, and you will not be able to see any spots on visualizing the plate. Too much, and the plate will be overloaded and no separation will be apparent. One way around this is to make 3 separate spottings on the baseline, the first with only a small amount of solution, the second with about 3 times as much, and the third with 3 times as much again. In this way, you are likely to get at least 1 spotting with the correct amount of material. Remember, the TLC is an extremely sensitive procedure, and it is very easy to overload the plates. The chromatography tank is prepared from a 250 or 400 milliliter beaker with a lid made from a watch glass or petri dish. The inside of the container is lined with filter paper to help saturate the atmosphere with solvent vapor. Fold or cut a piece of filter paper to produce a flat edge and place the flat edge along the bottom of the beaker. Leave a gap in order to see when plate development is complete. Add sufficient developing solvent to leave about half a centimeter of solvent in the bottom of the tank and wet the filter papers thoroughly. Swirling the solvent onto the paper will help you do this. When the filter paper is completely wet, the developing tank is ready to use. With the sample spotted onto the plate and the TLC tank charged with solvent, it is time to carry out step 5, develop the plate. Using the tweezers, place the TLC plate carefully into the tank, making sure that it is the correct way around with the baseline at the bottom, and allow the back of the plate to lean against the sides of the container at a slight angle. The baseline must be above the level of solvent in the bottom of the container. Make sure that when you put your TLC plate in the solution, that the pencil line is not touching the liquid in the beaker. It is important that the level of this solvent does not reach the level of the spotted sample. Otherwise, the sample will be dissolved off the plate instead of being carried up it by the rising solvent. Allow the solvent front to rise in a horizontal straight line up the plate by virtue of capillary action until it reaches about a centimeter from the top. If the solvent front is not straight, the analysis should be repeated on a new plate after checking the filter paper lining the tank has been thoroughly wetted with solvent and is not in contact with the adsorbent at the edges of the TLC plate. When the solvent front, that is, the line between the wet and dry, is about 1 centimeter from the top of the plate, carefully remove the plate from the developing tank, again using tweezers. Mark the solvent front with a pencil, not a pen. Allow the solvent to evaporate and the TLC plate to dry. We are ready to visualize the results. In this example, the material being analyzed was colored. Most material is colorless, and it will be necessary to treat the plate in some way to see the spots. A common method of analysis uses a combination of observation under ultraviolet light and staining with iodine vapor. Ultraviolet light is non-destructive to the compounds on the plate and can be used immediately. Be careful. Never look directly at the light source. Frequently, an inorganic fluorescer, zinc sulfide, is added to the TLC adsorbent. When viewed under short wavelength light, the zinc sulfide in the adsorbent will fluoresce green. Consequently, a TLC plate possessing fluorescer will show a series of dark spots on a bright green background when viewed under short wavelength light. While the TLC plate is under UV light, note the positions of any spots you see by drawing around them lightly with a pencil. Sometimes, some spots do not show up using UV light. In such a case, you can visualize them by using an iodine chamber. An iodine chamber is prepared by placing a few crystals of iodine and a small amount of silica gel into a wide-mouthed screw cap bottle with a lid. After standing the plate in this chamber for about 30 minutes, the presence of any eluted compounds are revealed by the appearance of dark brown spots on a light brown background. In the final step, the relationship between the distance moved by the compound spot and the distance moved by the eluting solvent is recorded. This measurement, the retardation or retention factor of the specific compound, is most commonly referred to as its RF. Measure the distance that the compound moved by recording the difference between the baseline and the center of the compound. For this example, it is 74 millimeters. Then, measure the distance the solvent moved by recording the difference between the baseline and the solvent front. For this plate, it is 100 millimeters. Calculate the retention factor, 74 millimeters divided by 100 millimeters, or a value of 0.74 for this sample. RF values are not absolute but relative. Because it is virtually impossible to standardize the activity of the support on the TLC plates, the application of RF values from one analysis to another is useful primarily to indicate the likely region to look for a compound on a TLC plate. When the TLC is developed in conjunction with an authentic sample of the compound, a so-called standard, the RF value is more accurate. If an authentic compound is available, identity is best demonstrated by the technique of co-spotting or double spotting. Since the unknown compound is usually valuable, the preferred procedure involves spotting roughly equal amounts of the unknown and the authentic compounds onto exactly the same place on the baseline, using different micropipettes, of course. Usually, the pure unknown and authentic compounds are also run on the same plate, either side of the mixed spot. In this example, it is already apparent that unknown U is not the same compound as authentic A. Thin layer chromatography is a valuable analytical tool. Let us review the 7 steps of this useful technique.